Okay, next talk given by Fu. The topic is I/O framework, perhaps.
Okay, hello everyone. I'm Shiyuan from HAPS Computing Center and the Institute of High Energy Physics Computing Center. And the talk I will talk about today, the high throughput data I/O framework for HAPS. First, I will give you an introduction for HAPS. HAPS is a high-energy photon source built by Institute of High-Energy Physics in China, and it includes more than 19 beamlines, and it will generate a huge amount of data. Such huge amount of data will give great pressure to storage and computing. So a team developed a framework named DESI. DESI is a data analysis software framework designed for HAPS. It has many models to meet the data processing requirements of such advanced scientific facilities. And it has data object management model and the scalable cluster computing engine for high throughput data I/O and the power to support for different scales data processing. What's more, it also has the interface and the developing environment for scientific software integration and development. And my work is focused on the data engine. And data engine my report is going to talk about the data engine in DAISY. Among the different parts in DAISY and the data engine mainly work with the workflow and the computing engine. So it should provide a unified interface for different applications and support parallel computing. It can read the data required by the computing nodes and write the result into the disk in order. It can read data from different sources and in different formats and write data in multiple formats to disk. So main goal of the data engine is to unify the difference caused by different applications and data and optimize the I/O speed. First, so we design and implement the HAPS I/O optimization method focus on the three steps. First is focus on to address the diversity applications of HAPS to show the differences in underlying data source or data format. We design and unify the I/O interface. Furthermore, to speed up the I/O speed during the batch processing, we use batch processing acceleration or parallel acceleration methods. And the last, to further avoid the I/O bottlenecks caused by data writing and reading on disk, we introduced the streaming processing I/O in DAISY. First, I will talk about the unified I/O interface. It can unify the difference caused by different application and data formats. By using this, user can not concern about what kind of the format they are reading. The interface can automatically identify the I/O methods corresponding to file methods, allowing the same application to read different data formats without changing the parameters in the I/O interface. The only thing you should do is to change the value of the dictionary. It looks like a configuration. What's more, we also provide tools for converting between different data formats, such as HDR5 and TIFFs. Additionally, we have integrated a series of data batch processing acceleration methods in the data acceleration. For data formats such as HDR5, we use direct I/O to allow data to be read directly into a pre-allocated memory space to avoid additional time consuming for memory copying. And we also provide a multi-threading acceleration library for TIFF. What's more, we also can speed up applications computing speed by asynchronous I/O, such as applications as HepCity. And we also has a data perfecting strategy it's based on producers and consumer model. And it's because that the application can determine the data being read in the next round. And to better management the memory space, we set a perfect queue to control the amount of data being read. And then we want our interface have the ability to support parallel computing. So we have to address such issues such as how to partition data, how to access data, how to work with the computing engine in DAISY, and how to ensure the order of the computation result in such a distributed computing environment. So first, for partition, we introduce the dimension parameters to determine the splitting method and block size. So the batch size means the total amount of data that our process needs to be read. So in this meaning, we can use this interface, and users can not influenced by the number of process. And for data access, we set a global process count and current process indexing. Our interface can determine the splitting method based on these parameters and identify the data block that needs to be returned based on the data index. And those information are passed by the computing energy. The computing engine in DAISY can process the global process count during the initialization phase of low data. And the low data is a function in DAISY data engine. And in this way, users do not change the original interface usage, only add some parameters to the configuration dictionary. It's convenient for users to use. In the last, for writing, because in different data formats, the data structure is different, such as for HDL file, it may has many projections in one file, but TIFF, it only has one projection. So we add a file name template to ensure the consistency in the writing interface for different data formats. And we can ensure the ordering of parallel result because we add the process index as prefix in the file names. And in our DAISY, we also provide workflow templates and basic I/O functionality examples for users and developers. And next is DAISY Stream I/O. For now, all the computing is based on data is processed after being written to disk. So we want to introduce Stream I/O to avoid I/O bottlenecks caused by writing data to disk and then reading it back by implementing a data streaming approach. First, we design the whole structure based on Flink and Alexo. Flink is used for receiving data streams from different DAQ systems. It can parse arrays, assembling, and performing some simple processing. And then the result is written into Alexo. It's a distributed memory layer. It's used for temporarily storing the data processed by Flink, and it can be accessed by the computing platform. And based on the platform, we developed a unified model. It has access powers and parsing data and management. In the management, we can define the data storage path, which can be only one path users need to find. And we also designed the DAISY streaming data structure. It established the mapping relationships with the DAQ streaming data structure. And in our DAISY data engine, it can be parsed automatically with different DAQ data. And there are 3 tabs in the streaming I/O. In the receive stage, users can control the number of partitions and the number of data streams contained in one file through the parameters to avoid frequent small data reads and writes, because different applications have different patterns. For example, for trials, no partition is needed, and with each stream is in a different file. And hep-city partitioning is possible, and multi-streams sit in one file. To store the streaming, we have mixed deployed of the Alexo and Flink. Thus, the worker of Flink and the worker of Alexo is deployed on one machine. Its aim is for better write speed, because there are it avoids another transfer in the network. And we agree on the construction strategy of file path and file name in Alexo for users. To exercise, because we know the rules how we constructed the path, we can get the file path we want to read without list the dictionaries. So based on this list of these files, we can read the files in order, and we will wait if a file does not exist. So the users can read the file by add some related case to the configuration to ensure the consistency of the DC-I/O interface. Here comes to the conclusion. First, we provide a unified I/O interface to the computation, show the underlying data difference. Second, we speed up the batch process by parallelizing and such methods. And the last, we introduced the all-stream data I/O to avoid the I/O bottleneck and support online processing. That's all. Thanks for your time.
Good timing.
Thank you for the presentation. What is the relationship between DAISY and the Mamba data broker?
Yeah. The Mamba data worker is the DAQ control system, and our DAISY is mainly focused on the data processing, and because there will be a huge amount of data, and it needs a lot of computing resource and storage resource, and we can, by integrated the applications into DAISY, we can speed up its calculation and use this resource well.
So DAISY is receiving the data from the Mamba data
Yeah,
broker? Okay.
yeah.
Thank you.
I mean, to process the data, you then need extra metadata. How do you ensure the metadata is coming through?
Stream.
Yeah, the stream.
At first, the metadata is included in every stream produced by DQ, as Mamba data worker. It can be included in a JSON format. It has metadata such as beamline ID, beamtime ID, this metadata, and has experiment data produced by the DQ. And it can be serialized as binary data to DAISY, and DAISY will process it.
Okay, thank you.